All right, so we'll begin. We are continuing on in our discussion of hypothesis tests. Okay, and so today we're going to take a look at hypothesis tests for P, the population proportion based on one sample. Okay. All right, let me have you guys settle down, please. Okay, so on Monday we kind of set up the general framework, the big picture idea for hypothesis testing. We said, we start off with some kind of claim or assumption. We use the assumption to create our idea of what to expect. And then we look at the data, what we observe, our reality, and we compare what we observe versus what we expect. If they are similar, then we have no reason to doubt our assumptions. If they're very different, then that gives us indication to doubt our assumptions. And the way we measure how similar or how different they are is we say, if we assume, if our assumptions are correct, what is the probability of us observing our data? If there's a high probability of observing our data while our assumptions are true, then we're okay. If there is a very low probability of observing our data while our assumptions are true, then that gives us indication that our assumptions are wrong. Okay, well, I'll kind of recap that in a moment. But today we're going to get into the kind of the steps of carrying out a hypothesis test. And in this case, we're going to look at the first one, hypothesis test for P, the population proportion based on one sample. And the 4 stages, we'll say 4 stages of hypothesis testing. We can list them off. One will be make hypotheses. Stage 2 will be some preparation. 3 will be calculations for a p-value. And the 4th stage will be make a conclusion. And once again, let me just kind of give us the big picture idea. Because as we work through these steps, it's easy to lose sight of the big picture goal that we have. The big picture idea is, we begin with, a hypothesis, okay, that we assume to be true to come up with an idea of what to expect. Create our expectation. We compare the reality, our observed data, to our expectation. Okay, and then we ask, what is the probability of observing our data if our assumptions are true, are correct? Okay, and this probability, the probability of observing our data if our assumptions are correct, that's known as the p-value. Okay, and what we said is if the p-value is large, okay, we have no reason to doubt our assumptions. And on the other hand, if the p-value is small, this gives us reason to question, or reject the assumption. So that's the big picture context. We want to know what's the probability of our data if our assumptions are true. If that probability is high, we have no reason to doubt our assumptions. If the probability of our data is low, that gives us a reason to question or reject the assumptions that we made. Yes? The assumptions we make is going to be our null hypothesis. That's what we use to, that's what we assume to be true, the null hypothesis. Okay, so I'm going to get into each of these steps, stage 1, 2, 3, and 4, but don't lose sight of the big picture here. All right, so part 1, the hypotheses. Okay. So the null hypothesis we write as H0, and the H0 is going to be P is equal to P0, where P0 is just some number that comes from our question. Important note, the null hypothesis always has an equal sign. The alternative hypothesis HA is P is not equal to that value, or is P is less than that value, or P is greater than the value, okay? The choice of not equal, or greater than, or less than depends on how the question is written. Okay. So, for example, we can say that, you know, someone claims that the bucket is 18% green. Or we'll say 17% green M&Ms. Okay? Someone claims that the bucket is 17% green M&Ms. All right? And then you gather a random sample. A random sample from the bucket. We'll say the random sample has 120 pieces. And 25 pieces are green. Okay. And so the question is, does our sample provide evidence that the proportion of green M&Ms in the bucket is actually higher than 17%? This is the question. Okay, so we're saying someone claims that the bucket is 17% green. When we take a random sample, we get 25 out of 120. Okay, 25 divided by 120 is like a little under 21%. It's 20.83%. And the question is, does that mean the bucket is actually over 17% green? And so in this case, our null hypothesis, what will our null hypothesis be? The null hypothesis is that P is equal to 17%, because that's the claim that we are testing, right? And then the alternative hypothesis will be what? Yeah, because here it says is actually higher than 17%. And so our alternative will be that P is greater than 17%, okay? So I'll write the question asks if P is higher than 17%, so we use P greater than 0.17. Okay? If the question was written in another way, do we have evidence that the proportion of green M&Ms is different from 17%? Then we would use a not equal sign. Or if it said, do we have evidence that the proportion is less than 17%? Then we would use the less than sign. So on and so forth. So that's how that works. The setting up of the hypotheses. Is this okay? All right. So once you have your hypotheses set up, then we will go through and we do a preparation step. Okay. Okay. Preparation consists of identifying summary statistics, or identifying your necessary, we'll say identifying statistics and values. Okay, and so for a hypothesis test for P with one sample, we need P0, the population, the value in the null hypothesis. We need N, the sample size. And we need P hat, which is going to be X divided by N, the sample proportion. That's our, those are the statistics and values we need. The next part is identify your significance level. Significance level is called alpha. which has the Greek letter. It looks kind of like the letter A, but it's a little bit different. Identify the significance level alpha. So alpha is the point at which we decide if the p-value is large or small. Okay, so alpha is kind of a, the value that determines if the p-value is large or small. Okay, so the p-value being the probability of our data, and earlier on we said the general idea is that if the p-value is large, then we have no evidence to, or we have no reason to doubt our assumptions, and if the p-value, if that probability is small, we have reason to doubt our assumptions. How do we decide when the value is large or small? That's going to come down to our choice of alpha. So alpha is kind of like a line in the sand. It's kind of an arbitrary line. And it's like, are you tall enough to ride the roller coaster? And it's just, 42 inches or whatever. You're taller than that, you can ride. If you're shorter than that, you cannot. Right? And so that's what we have. The most common choice of alpha is 5%. Okay, so if we'll say this is our default value. If alpha is not specified in the problem, you can assume that it is 5%. If excuse me. If we or the alpha might be, the problem might specify what alpha to use, what significance level or alpha to use. So that's what we have. So if alpha is not given, assume alpha is 5%. Okay, and then the last part will be check the conditions to use the central limit theorem. And so that's what? Random and independent condition. The large sample condition. And the big population. Okay, I want to say something. This is an important step, checking the conditions. However, when it comes to writing exams, it's hard to write questions where you're supposed to check the conditions as part of what you need to be doing in terms of, basically, I felt like I was writing traps if I asked you, do the calculation, find the standard error, but then later on it was supposed to be, oh, actually, I was just kidding. You aren't supposed to find the standard error because the conditions for the central limit theorem don't apply, so haha, I tricked you. It didn't feel quite fair to do that, so so for the final exam, kind of like for the midterm, I'll have a separate section where you check conditions, and then when I have you do questions like what's the standard error, or what's the z-score, or whatever, you can assume that the conditions are met. Okay, so is that okay? So that's how that will work. Okay, but in real life, it is important to check your conditions. Okay, in tests and stuff, just for the sake of doing them, the conditions will be met. Question?
So you said you're not going to do what?
I won't have tricky questions. Okay. Well, okay, I shouldn't say that. I won't have trap questions where I ask you to find the standard error, but the true answer was the conditions weren't met, therefore we're not supposed to find the standard error.
But you were talking about in real life, right? And so like in real life, we're not going to be solving a statistic problem for a test, but we might be.
Yeah, in real life, you're supposed to ask yourself, can I use the central limit theorem before you actually go on and use the central limit theorem? Okay, so in real life, you do need to check your conditions because you can't just say, oh, I'm going to use the central limit theorem. That's what I learned in Stats 10. Okay, you have to make sure what you learn in Stats 10 is you're supposed to check to see if you can use the central limit theorem. Okay, part 3 is calculating your p-value. And calculating the p-value itself can be broken down into a few subset steps. Okay, so I'll say part 3a will be find the standard error. The standard error is given by square root of p0 times 1 minus p0 divided by n. What was p0 again? This is the value from the null hypothesis. Okay, so in our most recent example, the value from the null hypothesis is 17%. Okay, once you find your standard error, the next part will be get your z-score. The z-score is in the form of what we observed minus what we expected, kind of our reality versus expectation, divided by the standard error. And in this case, what we observed is p hat. What did we expect to see under our assumptions? We expected to see the value p0 if the null hypothesis were true. And then we're going to divide that by the standard error. So this is what we get. And then once you have a z-score, what do you do next? You will look up the z in the table, okay, to get a p-value. However, what we do depends on the alternative hypothesis. Okay, so how we get the p-value depends on the alternative hypothesis. Okay, so I'm going to list off some rules here. If the alternative has a less than sign, the p-value is equal to the area to the left of z. If the alternative has a greater than sign, the p-value is equal to the area to the right of z. And lastly, if the alternative has a not equal sign, the p-value is equal to 2 times the tail area. And we define the tail area as equal to the side going away from 0 or in other words, that is to say, the tail is to the left if z is negative, and the tail is to the right if z is positive. Okay. And so this is how we get our p-value from our z-score. Okay, so it very much depends on what's in the alternative hypothesis. If we have a less than sign, it's to the left. If we have a greater than sign, it's to the right. And if we have a not equal sign, it's 2 times the tail area, where the tail area is the side going away from 0. Okay. Do you guys get all that down? Yes, question.
Could you possibly draw the tail area?
Draw little pictures here.
Yeah. Like I don't know which part of the tail area.
So okay, tail area. It's just always the side going away from 0. So let's say you have let's say z is negative, right? So you have like negative 1.3. The tail area is going away from 0. It's going to be this side. This is the tail. But if you have a positive z, and so we have 0, and then we have positive 2.1, then the tail area is going away from 0. It's to the right. This side is the tail. Is that okay? So it's tail is to the left if z is negative, tail is to the right if z is positive. Yes? Uh-huh. I'm sorry?
For the beginning, you said it's less than and greater than, and the last one you said it's not equal. If greater than is not equal also. So why is different?
Wait, is greater than the same as not equal? No, wait. What?
I don't understand because the first you say less than, right? Less than also is not equal. Why you have two different?
So, okay, I just want to make sure I understand your question. You're saying less than is the same thing as not equals? Okay, that's technically not true, okay? If something is less than, it does mean that it's technically not equal to that thing. However, not equal considers the possibility that it is greater or smaller than. So, so someone says the bucket is 17% green M&Ms, right? And we might be testing the claim, or we might be testing, is it actually higher than 17%, okay? In that case, we are only interested if our data supports the idea that the proportion is actually higher than what we've claimed. And we will not be upset if it's actually lower. So maybe here's a better example, right? Let's say, you know, some advertiser says, you know, if you give us a call, you'll save 15%, okay? And then they'll say, on average, you'll save 15%. And you're like, okay, I want to test this out, right? And you give them a call, and you do the math, and it actually turns out you're going to save 18% on average, or something like that. Are you going to be upset that this is what happened? No, okay? You're going to be like, oh, that's great. If anything, they're not advertising strong enough, right? And so we don't care if the actual savings is higher than 18%. But if they're claiming you're going to save 15%, but then when we do the tests and everything and it turns out the average is actually like 14% or 13%, then we might be upset, right? So in this case, we're only interested if the actual data is lower than what they claimed is going to happen, okay? And so in that case, we're only interested on one side of the equation, not both sides. That's what we have going on here. Maybe with some examples in the future and just more exposure, it'll work out. Okay, I know you don't seem to have a pleased look on your face right now regarding what the explanation I just gave. I'm gonna keep going here and just give you the step 4, and then you know, as we work through examples, I'm hoping it will clear up. But sometimes when we do hypothesis tests, we're only interested in one side. Okay, so number 4, we're going to make a conclusion. I've got a lot to write here. So what we do is we compare the p-value to alpha. Okay, and if the p-value is greater than alpha, then that means we consider the probability of our data to be high. We consider the probability of our data to be large. It's bigger than alpha, so we're going to say it is large. So that means we have no reason to doubt the assumptions that we made, the assumptions we made to create, our expectation. Okay, so we have no reason to doubt the assumptions we made, or in that case, you know, that being the null hypothesis. So the summary conclusion is if the p-value is larger than alpha, we do not reject the null hypothesis. And on the other hand, if the p-value ends up being less than alpha, we consider the probability of our data to be small. Okay. And in that case, it means our data is unlikely to appear if the null hypothesis were assumed to be true. And so the fact that we did see our data tells us that our assumptions are incorrect. And so that means, so we will reject the null hypothesis. Okay? And so the summary line of that is if the p-value is less than alpha, we reject the null hypothesis. Okay. Okay, so I'm going to work through an example here. And I'm hoping to squeeze in a couple clicker questions here, so we'll work quickly here. All right, let me swing back here, and I'm going to just copy this example that I first brought up here. Okay, so we're going to say someone claims that the bucket is 17% green M&Ms. Okay, we gather a random sample from the bucket. The random sample has 120 pieces, and 25 pieces are green. And we ask, does our sample provide evidence that the proportion of green M&Ms in the bucket is actually higher than 17%? Okay, so what we're going to do is we're going to work through the 4 steps of hypothesis testing. So part 1 is make our hypotheses. And we did this earlier, and we said the null hypothesis is that p is equal to 17%. Meanwhile, the alternative hypothesis is that p is greater than 17%. The next part is we're going to, we do our preparation. Okay, so I'll just go ahead and say conditions are met. Alpha is not specified, so what is the alpha that we're going to use? 5%, that will be the alpha that we use. And then we need to identify these values, p0, n, and p hat, which is x over n. So p0 is the value in our null hypothesis, 17%. N is our sample size. 120. P hat is our sample proportion. 25 divided by 120, I get 0.20833. Okay, and so now I will throw it to you guys. And part 3 is do your calculations. So the first part is I'm going to ask, what is the z-score? Okay, now you got to do your standard error first, but what is your z-score? And you have, here are your answer choices. Your answer choices are okay, so go ahead and work through that. I'll give you guys maybe like 2 minutes to do it, and then we'll take a look at our solution. Okay, I'm about to stop the timer. So I'm going to click stop here, and let's take a look. And 92% of you got it correct. Let's take a look. Okay, so in order to get our z-score, we first have to find the standard error, which is going to be p0 times 1 minus p0 divided by n. So the value we use is 0.17 times 1 minus 0.17 divided by 120. And when I punch all of that out, I don't actually know what I get. 0.17 times 1 minus 0.17 divided by 120. I take the square root of that. I get 0.0343, something around there. Okay, my z-score then is p hat, what I observed, minus what I expected from the null hypothesis, divided by the standard error. So I have 0.20833 minus 0.17 divided by the standard error, and I get positive 1.12. So that's my z-score. Okay, so with that in mind, the next question is, so my z-score that we found, z is equal to 1.12, and so the question now is, what is the p-value? Okay, so your options for the p-value are 0.8686, 0.1314, 0.2628, and 1.7372. So these are your options for the p-value. So this is another clicker question. Go ahead and try this out. So consult your notes and see, you know, the p-value does depend on the alternative hypothesis. So, okay, I'm about to hit stop. And we'll take a look. And indeed, that is correct. So when we look at our hypotheses, we have p is equal to 17%, but everything depends on what is written in the alternative. And the alternative says that the proportion is greater than the alternative, 17%, okay? So the alternative has a greater than sign. So our p-value is equal to the area to the right of z. So when we look up z in the table, you know, we're at we go to 1.12. When we look up z in the table, we find 0.8686, but we want the area to the right, so that's 1 minus that, and we get 0.1314. And so that is our answer choice. Okay? If the alternative was p is not equal to 0.17, then our p-value is equal to 2 times the tail area. In this case, the tail area is the side going away from 0. Okay? The p-value is the side going, tail area is the side going away from 0. So my p-value is 0.1314 times 2, and I would get 0.2628, which would be answer choice C. Okay? That's if the alternative had a not equal sign. Okay? But again, just pay attention to what is written in the question to determine your alternative hypothesis, and depending on what's written in the alternative, that will decide if you use the left, right, or double. Yes? What? So the picture going on, let me have you guys, somebody's talking back there, and let me just have you stop, please. So the idea here is we have 1.12 and then negative 1.12, and we're basically shading in both sides, because the idea for us is we want to see if it's more than the given value, or on the flip side, just as distant, you know, far away on the lower side. That's the idea for a two-tail test. Okay, that's what we have for getting our p-value, and then the last part is making the conclusion. All right, so our conclusion is that the p-value is equal to 0.1314. Earlier on, we've established that alpha is going to be 0.05. So when we compare, we get the p-value is greater than alpha. What does that mean? That means if the bucket were truly 17% green, or you know, if the null hypothesis were true, then it would be possible. It would be possible for a random sample of M&Ms to be, you know, 0.20833 green. Okay, that's what we observed. Okay, and this kind of random sample happens with probability equal to 0.1314, which is not small. Okay, so what we observed, is not very different from what we expected. Therefore, we conclude not to reject the null hypothesis. Hang on, guys. And we would say we do not have evidence that the proportion of green M&Ms in green M&Ms in the bucket is higher than 17%. Okay, we'll end there for today, and we'll see you guys on Friday.